reflection notes starting on page 1, and it says the formulas for magnification are m equals hi over ho, which sort of makes sense because if your image is twice as big as your object, you would say your magnification is 2. You could also use the formula negative di over do. So you got hi ho and di do. Now, if the image height is 10 and the object height is 5, you got to find the magnification. So we're just going to simply take hi over ho. So it says my image height is 10, so I put in the 10 for the hi, I put in the 5 for the ho, and you get hi over ho, which ends up equaling 2 times. And once again, that is why the 7 dwarfs are twice as small as Snow White. Hi ho, hi ho. Now, the image distance in this case is 5, and the object distance is 10, so you can also use negative di over do. So you put the negative 5 in for the di, the 10 for the do, and you get a negative 0.5. Now, what's the negative mean? It's upside down, very good, and or inverted for the big words. And 0.5 means it is smaller. Great job. Okay, now that Morgan has sorted her slices, what 3 characteristics are known about the image in a flat mirror? Well, if you look at this flat mirror I have up here, if you realize even Kayla Brown is not magnified in this particular mirror. She's still the same size. She is virtual, which means she's not real. She's actually in the mirror. And then finally, she is upright, which is unusual for her as well. Well, next thing I want to talk about, and I was surprised at how many of you did not even realize that your rear view mirror on your, I'm sorry, this is not the one I'm doing yet. I'm doing how big the mirror must be for you to see your whole body. And for you to see your whole body in your regular house mirror, your mirror has to be about half the height that you are. Because what's going to happen here is that your feet, the light's going to reflect off your feet, hit the bottom of the mirror. So if the bottom of the mirror is directly in line with your waist, the angle of incidence has to equal the angle of reflection. So we're talking this angle right here has to equal this angle right here. And so you're going to bounce that light ray from your feet directly up into your eye. Okay, the next thing we want to talk about is how does a rear view mirror in a car actually have day and night settings on it. And what you have here is the fact that most of the reflection comes off the back of the mirror. So like this mirror I'm holding in my hand, it's silvered on the back. So you got 96% of the light comes off the back mirror, silver part. So during the daytime, what you can have is you're going to have a light ray come in here. It's going to get bent up slightly, hit the back of the mirror, come back, and then get refracted into your eye. And since it's daytime, you got about 96% of the light doing that. Well, at nighttime, when you got those truck drivers or somebody just wanting to be mean and shine their bright lights right in your rearview mirror, it gets a little bit annoying. So what you can do is you can bend your mirror up. And some of you just said you hit the little button on the mirror and it goes down. Okay, but one way or the other, it's now going to bend that mirror one way or the other. And when you do that, now all that bright light's going to get reflected on top of the roof above your eye, so it doesn't go in your eye. And where you get the light from is from the reflection off the front part of the glass, because the mirror is glass, and then on the back of it, it's silvered. So you only get 4% of the light being reflected off the glass, and it simply reflects right into your eye like that. So the light you see is a lot dimmer, but since it's bright light, you can still see that there are cars behind you. So once again, during the day, the ray reflects off the silvered back of the mirror and reflects into your eye. During the nighttime, the tilt of the mirror so the ray reflects off the front glass instead of the mirror for the dim image. So a concave mirror is like the one I got holding in my hand. It's one where it actually caves in. And the image point is going to be halfway between the center of curvature and the center of the mirror. So let's draw this and see what we can make some sense out of it. Okay, so if you look at this note right here, it says the image point is about halfway in between the center of curvature. So if this whole mirror here was round on a great big round circle, center of curvature would be somewhere around there. And halfway between the mirror and the center of curvature would be where this is going to focus all of this light. So when I have light coming in from the sun, I'm going to have these rays coming in like this. Okay? And when it bounces here, it's going to go through the focal point. A ray coming in here like this will go through the focal point. Okay, is that making sense? So they're all going to focus these rays down through a focal point. So if I put an object right here, what can you do to it? Burn it. So what's going to be great about this is that the mirrors are going to work the same exact ways as the lenses. So Morgan, you were saying, where's the concave and convex mirror in the book? And I said there isn't. So you can just use the same rules. So if I wanted to write the 2 formulas for finding the focal point where all the rays intersect, it's simply the center of curvature divided by 2. You could also say the radius divided by 2. Or you could use that same formula we used yesterday of 1 over dou plus 1 over die equals 1 over f. Once again, if the image is positive, then it's going to be real. It's going to be in front of the mirror. So I'm going to be able to take that candle like I did the other day and project an image right there. So I'll do that for you in just a second. But the problem is the candle's going to end up being upside down. It's going to be inverted. So once again, if the magnification is negative, the image is going to be upside down or inverted like I just showed you. And if the magnification is less than 1, the image is going to be smaller. All those are the same as yesterday. Now what's really great about these ray diagrams is the fact that they're all the same as the lenses except for one. So you're going to draw parallel to the axis and it reflects back through the focal point. You're going to draw through the focal point and it reflects parallel to the axis. So those two are exactly the same. Now the third one though, you're going to draw it through the center of curvature, not through the center of the mirror. So draw it through the center of the curvature and it reflects back on itself. All right, so let's take a gander at this concave mirror. I'm going to draw it first so we can just follow the rules here. And it says a concave mirror has a focal length of 10. So I know this is 10. Well, if f is 10, what does c have to be? 20. Good job, guys. You learned that quickly. And then they say you're going to put an object at 25. So I'm just going to say that the object is somewhere around here. I think I'm drawing this a little bit pathetically, but that's okay. It says, first of all, draw the ray diagram. I'm going to do that before I do all the math. So let's just draw the ray diagram. First of all, I'm going to draw a line parallel to the axis, and it reflects back through the focal point. So let's draw the first one in red. So it's going to come off of here, go parallel to the axis, and then goes right through the focal point and comes down here like this. It should be a straight line unlike that. Okay. The next one is going to be drawn through the focal point, so it's going to draw an X just like we did before, and it's going to reflect parallel to the axis. So I'm going to take it off the top, go through the focal point down here, and then come down like through here. All right. And then finally, the last one says draw it through the center of curvature. Well, the center of curvature, let's see what color I have left. I'm going to draw this one in blue also. So I got ray 1 is in red. Ray 2 is in green, and ray 3 is in blue. Okay, so we'll do that. So the ray 3 is just going to be drawn straight through the center of curvature like so. Well, and where all of those intersect, what would you see? An upside down arrow. And that's what you just saw when I shined the mirror up on the wall, is that upside down candle. All right, good job, Emily. I'm going to use to find the image distance, I'm going to use 1 over dou plus 1 over die equals 1 over f. And it says it has a focal length of 10, so I'm going to go ahead and put in my 1 over 10 here. It says locate the image distance, so I'm looking for di. I'm going to put my di back in the formula here. For my object distance, it says it's 25 centimeters away, so I'm going to put in a 25 here. So let's find a common denominator. For 25 and 10, what would be a common denominator? Something like 50. Good job, Morgan. I got 50 there. Plus 1 over di. I'm sorry, this would be 2 over 50 equals 5 over 50. So hopefully we all remember how to get common denominators. If I multiply the 25 by 2, that gives me 50, so I have to multiply the top part too. So 1 over 25 is the same thing as 2 over 50. If I multiply the 10 by 5 to get 50, I have to multiply the top by a 5 also, so that gives you 5 over 50. I'm going to now subtract 2 50ths from both sides. And so that gives me that, oh shoot, I'm running out of room. 1 over die equals 3 50ths. Then what do you have to do? Flip it. So die equals 50 over 3, which comes out to be about 16.67 centimeters. So if you put your screen 16.67 centimeters away, you will see the picture of that little arrow. Now you got to figure out what the magnification is. And the magnification is negative di over dou. And so I'm going to put in my negative 16.67 and divide that by my object, which is 25. And that ends up being a total of, I now get a negative 16.67. So let's talk about this first of all, what all these things mean. Since the image distance is positive 16.67, is it real or virtual? Real. So that positive means it's real. Since the magnification is negative, that means it's inverted. And since it's less than 1, that means it's smaller. Okay, for a convex mirror, it's a little bit trickier because this time you're going to have the rays going out. I'm just going to draw everything above and below instead of trying to fit it all in like this. So with a convex mirror, it's going to be pointed this way now. I'm still going to have the object over here, so this will be something like the center of curvature. Gotta hope I'm doing this right. Okay, so it'll be center of curvature here. This will be something like the focal point right here. But over here, you're going to also have a focal point and center of curvature. Okay. Now, I want to let you know, over here on the left-hand side, is the center of curvature really there? No, because this mirror curves out. So you can't have the center of curvature over here. You can't have a focal length over here. Okay, so I'm going to get rid of those. And I'm going to put the object, I know it frustrates you. I'm sorry. Just scratch it out. Scratch it out. I'm going to put the object over here now. Okay. So let's follow those same rules as we did before. The first rule says you're going to draw the array parallel to the axis and reflects through the focal point. All right. Well, here's the problem with that. If I go parallel to the axis, it reflects through the focal point. So that means when it hits this mirror, it's going to reflect off like this, but you sort of have to use your imagination and follow it back through the focal point. Does that make sense? So your brain's going to see it in there. Okay. The next one goes through the focal point, but reflects parallel to the axis. So now I'm going to draw one, the green one. I'm going to act like I'm going through the focal point here. Okay, so I'm sort of aiming for the top of that arrow. So the arrow's going to come down here. It's aiming for that focal point, boom. When it hits here, it goes parallel to the axis like that. Okay, but your brain's going to follow it back a little bit differently than that. Okay, so I look like I was going through the focal point, and then it goes parallel. Right? And then lastly but not leastly, you go through the center of curvature. And so I'm going to take it like this, and the one going through the center of curvature simply bounces back on itself. Shoot, that was a good straight line. All right, so this one comes in, and it bounces right back on itself. So let's see what you're going to see in the mirror. Your brain is going to follow that ray here back like this. Okay, and if I would have drew that blue line straight, you would have thought that. Your brain simply follows this one straight back like this, like it's supposed to go. Okay, so where you have the red and the green and the blue meeting is all right in there. So what are you going to see in the mirror? You're not going to see a big blue arrow. You're going to see in the mirror a small arrow. So in the mirror you see a little tiny arrow. Okay, and that's why you can get the whole room in one mirror. And let's do the finally let's do the formulas for this real quick. I'm going to use the same exact formula of 1 over di plus 1 over dou equals 1 over f. Whatever I just said. 1 over dou plus 1 over di equals 1 over f. But the thing is now, your focal point's behind the mirror. So what do you got to do to that f? Yeah. It is a negative f. Great job, Luke. So we're going to put in a 1 over, what's it say the focal length is? 8. So we're going to put in a 1 over a negative 8. The object is placed 20 centimeters from, so the object is 1 over 20. And the image distance is what we are trying to find. So our common denominator is going to be 40, so this is going to be a 2 over 40 plus a 1 over di equals a negative 5 over 40. Subtract 2 from both sides, so now 1 over di is going to equal negative 7/40, I hope. Yep. negative 7/40. You then have to flip it, so di equals 40 over negative 7. So your image distance is a negative 5.71. It's negative because it's where? Behind the mirror. It's virtual, okay? And so it'll look like it's 5.71 centimeters. We're then going to do the magnification. Well, there's a couple different ways to do magnification. You could do di over do or high over ho. Let's do negative di over do. So you just got to be careful here because it's a negative times a negative 5.71. So I brought that negative down and I put the negative down here. The object distance was where was it? 20. Okay. So when you look in that mirror, you're going to see a little teeny magnification of 0.286. Since it's positive, what are you going to see in the mirror? Virtual image. Oh, wait, careful. Upright image, right? Upright. And you will also see it as, since it's 0.26, you'll see it smaller. Now, this is the type of mirror that you use in the side view mirror of your car. So when you look in it, you get a much bigger view, but all the objects appear what? Smaller, but they're upright. That's a good thing because you wouldn't want to see upside down cars. Okay. Now, the problem with them being smaller is when your brain sees something smaller, it thinks that it is farther away. So that's why they have to put the little sign on the mirror that says objects in this mirror are closer than they appear. Okay, we'll come right back to this. Before we let you go, I want to give you 2 little hints onto homework tonight. So if you're doing the AP problems from I forgot what page it is, 753, something like that. On page 753, you had problems number 15 and 29 were both a little bit rough. 15 is rough because you have to manipulate so many formulas. And what they're going to do on the first one, they're going to give you the object distance, which is something like, let's see here, I think the object distance on the first one that was given to you was somewhere around 18-ish, I think. I forget what I'm doing. Hold on here. They give the object distance, and they also give you an image distance. And on those problems, you have to, first of all, figure out the magnification of that, okay? Well, there's one thing that never changes about a mirror, and that's the focal length. So what you're going to do is they're going to say that you want the magnification to be 2 times, and they want it to be a real image. So what you're going to want to do is you're going to have to find DO and DI. Well, you have 2 unknowns here. Well, there is a formula that you can use to figure out one of the unknowns. And one of the formulas that never change is the focal length. So if you know if the focal length is equal to DI plus the inverse of DO, the inverse of DI plus the inverse of DO, what you're going to do is you're going to take the first image distance and the first object distance that they give you and plug that in first. So they gave you an image distance, I think, of 18, something like that. They gave you an object's distance of 152 centimeters or 1.52 meters. So figure out that focal length. Once you get that focal length, you're going to do the same formula over again. So bring this one down. So you're going to take that answer to the focal length and put it in here. And then what you're going to do is you're going to solve for one of the 2 unknowns. Now, let's talk about this here. If I got DI and DO and I don't want 2 unknowns, you can use this formula up here. Remember that M equals negative DI over DO. So if you want to find out what DI is, let's say, I can say that DI equals M times DO. And if you want M to be 2, I now have DI equals 2 DO. So what you're going to do is you're going to take this answer up here for F, plug that in again because the focal length of the mirror never changes. Then instead of DI plus DO, you're going to switch that formula around so that 1 over F, once again plug in your F, equals, instead of DI, I'm going to substitute in here. So I'm going to have 1 over 2 DO plus 1 over DO. And don't forget that's going to be a negative number down here, so it's going to be a negative MDO, okay? The last thing you have is number 29. So there is a formula in your book for this, and I want to go ahead and give that to you. Sometimes you'll have a lens that has two different curves to it. For instance, like a contact lens or an eyeglass lens. You might have a diverging lens, but it's going to look like this. It's still thicker on top, but the one radius will be like this, but the inside radius will be a little bit different. So it's still thinner in the middle than it is on the outside, but it looks more like a converging lens in a way. Okay, but it's not. It's still a convex lens. So what you're going to have to do here is a different formula, and we're going to get that focal length. We're going to take n minus 1. Now the reason for that is let's say this contact lens is made out of plastic or something of that nature. Plastic has a different index of refraction. So since air, I got a light ray coming in here that's going from air into the plastic, it's going to get refracted a certain amount. And since air's index of refraction is equal to 1, I'm going to subtract the index of refraction of the contact lens or whatever lens this is, that material, minus 1. And then what I do is I multiply that by the radius of the outer edge, so this outer edge here, and subtract from that the radius of the inner edge. Okay, so that'll give you the focal length of that lens.